everyone. My name is Rohan Singh Rajput. I'm a senior data scientist at Headspace, and today I'll be talking uh, about my talk, mindful personalization, building a recommendation system for a meditation app. So this will be our agenda. We'll talk about the introduction, uh, history of Headspace, uh, history of different models, the current state of the project, different challenges and opportunities. So before we start, let's discuss a little bit about Headspace. So what is Headspace? Headspace, we are a meditation and mindfulness company. We provide lots of online guided meditation contents, lots of audio content, video content to our user, so they can uh, it can help our user to learn meditation and also achieve mindfulness. This is the current layout of our app. As you can see, there is a huge opportunity for recommending content to our users. So this is our different types of tabs. So as you can see, the today's tab, it will be like a curated guided meditation for you. Then we have like a different kind of modules like meditation modules and sleep modules that can help you to help with your different kinds of needs. So a little bit of history about why we want to do personalization of our app. So we launched this project called Content Customizer in 2020 to counter the declining retention rate. Uh, Basically, what was happening, all of our user base was getting same editorial content, and we have over 1,000 contents that has to be served for over 2 million B2B subscribers. So it is very difficult to give our user all the content at the same time because of the limited UI space we have. So the hypothesis behind the project was how, if we can personalize experience for our user, or if we can provide personalized content to our user, that will lead to higher engagement. So to test that hypothesis, we created Content Customizer, which is our recommendation system that serves online personalized recommendation to our user. And it uses historical user item interaction data. So there are like three important concepts before you start any kind of machine learning modeling. So the first component is data. So we acquired lots of our B2B and B2C data. We created a feature store where we collected lots of user features like user tenure demographics and language information. And also we collected lots of item feature, which is our in-house content. We launched this experiment for both iOS and Android. We chose various evaluation metrics for different machine learning models like NDGC, hit rate, and for online evaluation, we chose randomized controlled trial, also known as A/B testing, which is a gold standard for testing online or establishing causality with high probability. Now, the third important thing is that after building these models, we wanted to serve this model. So recommendation system is not just the modeling, right? You have to create the entire system. And for that, we have to choose that what kind of training we want to do. So we chose like a nightly batch training. We used to send our predictions to prediction service, which is an internal service we created. And we also did lots of post processing after generating recommendation, like we fixed our sequence, remove popularity bias, and also remove recently completed contents. So let's talk about machine learning modeling here. So we deployed this model for both B2C and B2B customers, and it was also deployed for both iOS and Android platform. So the typical process behind is like we do first the data pull, we do overnight model training, we generate prediction, we send it to us, we do like lots of post processing of our inference, and then we send this data to prediction service. Now let's talk about history of the models, right? So we developed so many models, and there are few which I think will be very important for this talk. I chose here. Apart from these models, we also developed different types of models, including reinforcement learning and graph-based recommendation. But here we will talk about these three important types of models. So first model I want to talk about was Light FM model. Light FM model, the reason behind choosing Light FM model because it is first of all a very simple model to implement. It is a simple metric factorization model. What it does, like apart from traditional metric factorization, it also incorporates user and item features. As you can see on the top, that we are including user data as well as the item data. Uh, Let me start my pointer. Yeah, and then we included lots of like implicit and explicit feedback from the users. Because this is a metric factorization model, so usually it is very fast on GPU optimization because it's a simple linear algebra, and it's a very highly scalable model. We chose precision K and recall K as our offline metrics, and we ran an A/B testing uh, by focusing on our driver metrics we chose for this A/B testing was content start and content complete. So we wanted to measure that in control and treatment, what average content start and content complete we can get. Unfortunately, we did not get any statistical significant lift in this experiment, and we tried to figure out that what are some of the reasons could could possibly uh, cause this kind of performance. So we moved to the next model, which was a neural collaborative filtering model. What does this model do? That like it models uses neural network to learn user and item latent factors. So in the first layer, you can see that we have like all the user items, user features here, and then we have like all the item features, and we try to learn the interaction between this user item using this neural network collaborative filtering layer. Once we train our model, we generate inference and we send it to prediction service. The reason behind choosing like this neural collaborative filtering model was first, neural networks known for their non-linearity because they can learn like more complex relationship by introducing non-linearity to the system. The second thing, we can use lots of like metadata of items and users, so we can utilize our user item features in much more detail. And the third thing is like new NCF model can handle like sparsity, which is a common problem. Like usually for a typical recommendation system, we see that we have a limited user item interaction because uh, most of the user engage with very few of the content, and those are contents are very popular content. So in those sparse metrics, how to handle such a sparsity, neural network can actually learn those latent factor even with those sparsity. Now we chose again offline metrics as a precision K and recall K. And in this particular experiment, we found that we have 2% statistical significant lift for content average content start and content complete in our A/B testing. Now, even though this looks like a very small lift but the number of users we deal with, this kind of lift can provide significant increment to the engagement. Now, the third and final model we are discussing about is the TSAS rack model. Now, this is a completely different kind of model, which compared to what model we used in past. So this in this particular model, you leverage the sequence of interaction. So, for example, let's say example of this particular, uh, we have different kinds of movies here, like let's say a Man of Steel, Wonder Woman, Justice League, and Thor, and a user can watch like these movies in particular sequences. Not only we can utilize these sequences, but we can utilize like the time interval between the sequences. So if we keep like 10 days gap between these two contents and several month gap into different type of content, we can utilize these interval of like time intervals and also sequences. And based on these historical sequences, we can learn that based on like this current sequence, what will be the next more next content our user most likely will start or play. So, so the reason we chose model first, like obviously the sequential data. Second is the temporal dynamics, which I explained that we have like a different time intervals there, and we can extract that information and use it as a feature. And third is the transformer architecture, because transformer architectures are utilized for are optimized for uh, sequence data, and they can run in large computation parallelly on GPU. So this architecture was first of our choice. Uh, in this particular experiment, we made several changes. So because this is a sequence model, and also we wanted to learn more about like how to rank our content, because of the limited UI we have on the screen, we wanted to see that like how we can uh, get our best content on the top. So therefore we chose NDGC and hit rate K as our offline metric. And in this particular experiment, we achieved over 4.66% statistical significant lift in our A/B testing. Now let's talk about system architecture. So our system architectures is pretty simple. There are two important components of this system. Like first is the offline training and inference, and second is the post processing, or you can say real time filtering, right? So the top layer talks about this offline training. So first we collect all this historical data from different systems like M particle and amplitude. We dumped it to our like in-house database. In that in-house database, we train our model on like Databricks platform. And once we complete our training, we send our predictions to this prediction service. Now, we also keep lots of log of our model's metrics for monitoring and optimization. And once we send all our prediction, then our module service fetch those predictions and serve to our user. Now, in that in that process, if a user actually exit a content, recently exit a content, then we can actually remove that content using this real-time filtering process. That means what we can do that, like if you just recently played the content but you are not interested in that, we can use this M particle kinesis stream to remove that content. Now, there are different challenges we faced while building this model, and there are still some challenges we have in our production system. Some of the challenges I wanted to talk about are first is the feature space. That means like when you collect lots of this user item data, sometimes it is not rich enough to understand the user behavior. That means that you are not able to capture all the types of user behavior from this user data. We also had lots of subscription mismatch. That means that sometime what happened that one user can belong to multiple subscription category, right? The same user is in B2B and B2C. So it can also create like some kind of problems because one user can belong to like multiple subscription type. And if you're building a model for multiple type of subscription, then that could create like some kind of conflict. The third thing, important thing is here the sparse interaction. The sparse interaction means like there is a huge popularity bias in the content because historically we trained our like we serve our content as an editorial content. Everybody was getting same kind of content, and because of that few of the content got extremely high interaction or extremely high engagement, and there is a huge amount of content. So we have like this long tail problem where lots of content have a very low interaction and the few of the content has very high interaction, and that creates this sparsity problem in the system. The third and important thing is the uh, privacy and compliance. So privacy is very important because we are a healthcare company. We also are HIPAA compliance. So we take all our due diligence to collect only necessary information and do not include any kind of private information that can introduce any kind of like bias to the system. So that is also a big thing that how we have to handle those data, how we have to mask and de-identify our users, and what are the data points we should be collecting that can remain within the privacy and risk compliance framework. Now, another thing is that, like, apart from the user feature, we also have some of the issues with the item features also. So lots of our items was fragmented. So the thing is that, like, unlike Netflix or Amazon, our data is completely different, right? We don't want our user to keep engaged like all the time on our screen, right? Our contents are very different. We are a meditation company, so we want our user to come to the platform, do meditation, and then, yeah, then enjoy the rest of your day. So the type of content we have is very, very different. It's they have like a multiple types of uh, content types. For example, we have videos, we have like there's something called Wake Up, which is a playlist of multiple videos. We have like a lots of audio meditation, sleep meditations, sleep cast, sound cast, all this different kind of meditation. So to understand all those this content and then put into the system, it was very challenging task because sometimes one particular content can belongs to multiple types of categories, right? So we have to uh, segment those contents into categories, and we have to tag them that this is the particular content we want to serve on this particular tab, and this is the content we should be sending to this particular category. uh, so also lots of the features were stored in multiple system. So we have to make sure that we are collecting all those information from all the resources. So we collect important all the important features of our items. The second challenge here is the UI rigidity. So you can see that we have multiple types of screens, and there are like various types of content that cannot be removed or cannot be recommended on the app. So, for example, that the first content I'm talking about, this is the high performing content. This is the wake up. This is our wake up content, which means that every day user open this app, they will get like this new wake up video, and this is a very high performing content. So we cannot remove it, and it is also not recommendable because we generate on a daily basis. The second is the static content, that if a user start like a Headspace 365, they want to do like everyday meditation, and they have like a 365 days of catalog. So we want that particular meditation to be served to that user for all those 365 days, and that's why that particular slot can also be not removed or cannot be recommended. So we that actually reduces our surface area to recommend our content. Second thing is like we are using a single model for all of the places. So sometimes you need like because if you're using same model for multiple area, uh, it might introduce some kind of redundancy to the recommendation. And there is a like a there is a like a lack of explicit feedback, so we don't want to interrupt our user with asking like feedback that how whether you liked our content or not. So sometimes it is also difficult to understand that what is the particular reason user did not like this content, or why the user exited this content pretty early. Now let's talk about the opportunities. So there are like several opportunities to improve this recommendation, and we incorporated lots of them. The first is, rather than using this horizontal like vertical scroll design, we introduced is the shelf-based design, that rather than having like a single meditation, we have like this collection of meditation for each particular shelf. So you can see this horizontal scrollable content, which can be used for like we can create like this different kind of shelf for user, and that can also be personalized. We can use like a different screen for notification or recommendation, and we can also introduce like a recommendation in the search space also. So if somebody searching some particular type of meditation, then we can also provide like a search based recommendation and also collect that search data, which can help us to improve our content recommendation, which is pretty common in like lots of other systems like YouTube or you can say Netflix. In the modeling term, we wanted to optimize for long-term value. That means like we want our user to be, more mindful, and like eh, we want our user to be happy, and we wanted to optimize those metrics for long term. So habit formation is one of the things that if you, for meditation, if you do, it's kind of an habit. Like you have to build an habit like an exercise, and that's why we wanted to optimize for those kind of long term values. We wanted to incorporate multimodal feature. That means like rather than just using interactions and like this simple meta features, we wanted to incorporate text, images, audios in our recommendation system. Uh, there's personalized shelf ranking. So this shelf also can be personalized according to the user. So suppose if you have similar kind of need, that shelf will be shown on the top rather than like on the bottom. We are focusing lots on causal AI to get explainability. We want to be more transparent about our recommendation. If we are serving any kind of recommendation to our user should know that why this particular type of recommendation has been served and what type of data points we use to serve that recommendation. And we not only optimize for engagement, we wanted to optimize for novelty, diversity, and relevance. That we have different kinds of demographics. We wanted to like serve recommendation for all type of communities. We wanted to promote some of the novel content to our user that sometimes can be because of cold start issue might not get like that enough traction in first few days. And also we wanted to improve relevance, that if we are serving a certain kind of recommendation, that should be relevant to our user. Last thing is that we are not building just a very good model, but we are just building like a robust end-to-end system. So we want to incorporate multiple types of data from multiple streams. So for example, like impression data, that if the user is just scrolling on the content, that can we use that data, and rather than like click through rate and all those things, can we just by the impression itself, like we can utilize that particular data. We wanted to analyze different type of drift like data drift, model drift, and concept drift. So we can uh, all the time attentively monitor our recommendation, and if there is any kind of drift is there, like data drift or model drift, or any kind of concept drift, we can intervene in that particular scenario. The third important thing is smart caching. That means we want to reduce our latency. We want to cache like lots of this content which is stay relevant and serve to our user as soon as possible. The fourth thing here is like real-time inference. That means currently we are doing batch processing. That means we are training our model overnight and sending our prediction to prediction service, and then the prediction service serving them. But rather than having this kind of process, if we can like get all the real-time data of user while user interacting with the app, and can send this recommendation while while user is interacting with the app or in real time. The last thing is like we wanted to build an interconnected recommendation system. That means not only we want this recommendation system to serve on in app, but also for in other channels like for marketing, email, push, and notification. So our users can get like if our user do not uh, forget to meditate someday, we can email them about their daily schedule. We can send a push notification to them, and we can reduce the amount of noise we send to our user and only send relevant information, so our user can get full benefit of their subscription. So that's all from my side, and I would like to thank entire Headspace team who is part of this amazing system. And yeah, if you have any questions, please feel free to uh, email me or contact me uh, at rohan.rajput@headspace.com. Oh, thank you so much.